next speaker is Jean-François Lafont, who will talk about cubulating groups obtained via strict hyperbolization.
Okay, thank you for the invitation. It's lovely to be back in Rio. It was a little too lovely last night, but I'm still recovering. So what I'll be talking about today is some joint work with Lorenzo Ruffoni. And what I'll be discussing is sketching out the argument for the following theorem. So let X, or maybe let's sigma. Let's go with X. Let X be an arbitrary simplicial complex. And gamma will be, so we're going to do a procedure. So we're going to apply, so this is a strict hyperbolization procedure. And then we're going to look at the fundamental group of the space that we obtain out. So I'll spend some time discussing what strict hyperbolizations are. So then gamma is special cube rule. Maybe I should put in virtually. So what this means is, so i.e., so there exists finite index subgroup. So gamma naught, or lambda inside gamma, where lambda is pi1 of y, where y is a compact locally cat zero cube complex. Okay, so this is sort of the goal of the lecture. And I'm going to start out by talking a little bit about these strict hyperbolization procedures, because those feed into the proof. And so hyperbolization procedures are processes that take a simplicial complex. So the input is simplicial complexes, and output a locally cat zero cube complex. And this is actually done, so this is the original procedure due to Gromov. So simplicial complex, and here it outputs locally cat zero cube complex. So this drastically changes the topology, but it preserves some features. So things it preserves, so note changes the topology, but preserves some local topology. So the links in the cat zero cube complex end up being various subdivisions of the links in the original simplicial complex. Now, so the fundamental group of what you have here is a cat zero group. And then Charney and Davis built on this to develop a strict hyperbolization. And so So hyperbolization usually refers to this first part, even though these are not necessarily, the groups here don't end up being hyperbolic. Strict hyperbolization gives you a locally cat minus 1 piecewise hyperbolic complex. And so again, it drastically changes the topology at each of these stages, but local topology is maintained. Okay? So yeah.
When you talk about simplicial and cube complexes, which metric do you consider on that?
So here this is just combinatorial. Here the metric is each cube is standard 1, 1, 1 Euclidean cube. Yes. Whereas here the metric is well, piecewise hyperbolic, and then the induced path metric. Is that okay? Because when things get glued together, you might have multiple pieces, and so yeah. Okay, so now I'm going to focus a little bit on this because this first part of the story is not so relevant to the arguments we have. So let me explain how this process goes here. So the Charney-Davis process is a replacement. It's inductive. So goes by inductively replacing the cubes in your locally cat zero cube complex by piecewise hyperbolic, so by hyperbolic manifold with corners. So with piecewise geodesic boundary intersecting at right angles. So let me draw you the picture. This will be more informative. So anytime you see a vertex, you're replaced by a vertex. Anytime you see an edge, you're replaced by an edge. So those don't change. But now, when you see a square in your locally cat zero cube complex, you want to replace it by something that's hyperbolic. And the way you do this is you tack in a handle. All right? And so on. All right. So now, and so on means that you can then you have to make sort of compatible choices in higher dimensions. And so let me describe a little bit how this first process is obtained. So this space here, you can obtain in the following way. If you take your surface of genus 2, you can consider the following pairs of involutions on them. So let's see, maybe I'll do the front back. So here I'm drawing you the fixed sets of the involutions. So maybe one that goes like this, and then one that goes, so this is going to go all the way around. Is that all right? Folks see the two involutions there? So these are a pair of commuting involutions. So you have commuting involutions. So the fixed sets always intersect orthogonally. And then what you can do is you can pick a point here, look at the connected components of the fixed sets that pass through that point, and cut open along it. So if you cut open, so the connected components of the fixed set passing through the point here are, so I'll erase all the other components of the fixed set. You're left with the geodesic kind of running around, and then the geodesic that goes across. And if you cut open along those, you get a shape that looks like this. All right? Now you need to also be a little bit careful. You maybe want to make sure that the two sides have the same length, so these geodesics match. Though I guess that's probably not necessary for the, yeah, you probably don't necessarily need that. Then I guess it would be slightly longer. Could be longer and narrower, that's fine. Okay. All right. In higher dimensions, the way these are obtained, so in higher dimensions, you start with an arithmetic, so the simple type arithmetic. So simple arithmetic lattice. And your trees of Hn. And you can choose these so that you've got these commuting with n distinct commuting involutions on the quotient manifold, so on the resulting quotient manifold, and then you do this process of cutting open along all the various ones. Is this okay? People get this description of how we
Why they exist and commute?
sorry?
Why do they exist and commute existing?
So this is, yeah, so this is basically the point of the Charney-Davis paper, is to just construct these. And so the involutions they take are the usual ones where you flip one coordinate and yeah. Now there is a little subtlety here, because when you make the choice at the level n, that kind of forces what happens at the lower levels. So it's not clear, at least to me, whether there's an infinite family that's compatible. But for any given dimension, you can find a choice that works and is compatible with the lower ones. Okay. All right. And then the last thing then is, okay, so this kind of tells you how to replace cubes. Now, if the sides aren't the same length, or if you've got anything kind of funny like that going on, you might want to have some coherent way of making the choices. This is often done by taking the cube complex to be foldable. So if the cube complex that you feed in is foldable, so i.e., so this is going to be a cube complex here, maybe y. So there's a map from y to a cube of whatever the dimension of this cube complex is, which on each top dimensional cube restricts to an isomorphism onto this cube. Okay. So this is called a folding map. Then you can make a compatible choice. So if I call this guy here, so this is going to be h of 2 cube. So then what you can do is you can then form the pullback. So you've got your folding map. And this is going to be your h of y. Is this okay? So maybe, so this is the folding map. This map here I haven't described for you, but it's basically the map that collapses everything except the corners of the manifold, of the hyperbolic manifold you construct. So in 2 dimensions, this collapses everything in here down to a point. So all you're left with are the little neighborhoods of the corners, and those attached to give you a cube. And in higher dimensions, you do the same thing. Okay, so this is so you're basically just ignoring all the topology that you've introduced. This gives you this folding map, this collapsing map, and then you pull back. Okay, so this is the hyperbolization procedure. Now, a nice feature here. So this is it's a robust way. So this is can be used to produce many exotic examples, exotic manifolds. So for instance, so e.g., so you can use this to produce, aspherical manifolds with universal cover not Rn. I think here you need at least 5 for this construction. So this was done by Davis and Januszkiewicz. So most of these examples here I'm mentioning are due to Davis and Januszkiewicz. Other examples, so aspherical manifolds whose universal cover is Rn, but whose boundary at infinity is not a sphere. Okay, so these are other exotic examples. And where these come from, so here the idea in these is that you start out with a simplicial complex where there's some exoticness in the links. Okay, so with the non-PL, so here we want to start with exotic triangulations. So i.e., so e.g. not PL. And then if you remember back here, I mentioned that this process, they changed the topology, but they preserved the local topology. And you can kind of see that because of this pullback construction, right? All you're remembering locally, whenever you glue these things, you're gluing them together in exactly the same pattern as they were originally. So local topology is preserved. And so if you've got some exotic triangulation with something exotic in the local topology, that's going to propagate. So if you think of this sort of more theoretically, if you think of growing the boundary at infinity as a limit of larger and larger balls, then every time you pass through a point or a simple or a facet with some exotic link, with some non-trivial topology in the link, you're going to pick up, every time you transition through one of these points, you're going to be doing a connected sum with a punctured link. And so you're going to pick up more and more topology that can accumulate at infinity. So even though this one here doesn't look like it's a large-scale thing, I guess work of Siebenmann tells you that if the universal cover being Rn is equivalent to the boundary at infinity being simply connected. So this really is also a statement about the large scale. Is this okay? Are people all right with these? Yeah.
Both these examples can be made locally categorized one?
Yes, exactly. So yeah. So in the Davis-Januszkiewicz paper, they actually stopped here, since they were only interested in aspherical. But if you apply then the Charney-Davis, then you get examples that are, cat minus 1. Okay. All right. So pick up topology from exotic links. And then, so limit of spheres gives exotic topology. So that's the direction in which, so that's, and there's a lot more examples of things, weird things, funky things you can do just by playing around with different types of triangulations. In a different direction, if instead you start with a very nice triangulation, so all of these examples, when you try to produce weird examples, you want to start with weird triangulations. At the other extreme, if triangulation is a smooth triangulation, then this resulting locally cat-1 piecewise hyperbolic manifold, maybe I should say smooth triangulation of a manifold, then when you apply this process, the output has singularities. So when you glue these together, you know, I mean, you could already see this in 2 dimension. If you've got, you know, if you've got multiple squares attached together, you've got excess angle. Has singularities. Which Ontaneda showed can be smoothed out. Can be smoothed out while maintaining sectional curvature less than 0. And so the upshot here is this produces new examples of negatively curved Riemannian manifolds. Okay. So sort of in both cases, you get interesting things. This is due to Ontaneda. A few years ago. Sorry?
What is this smooth triangulation here?
So each simplex. So you start out with a smooth manifold, and each simplex is smoothly embedded. So
So it's extensive.
that's right. That's right. Okay, so this is all I wanted to say about this. How am I doing on time? 20 minutes? Okay. All right, so that's all I wanted to say about hyperbolization. So now let me talk about cubulations. So the goal now is to get this to act on a cube complex. So the goal is to produce, well, maybe let me back off a little bit. Okay, so to get, yeah, maybe I'll just go straight to, so to prove, so for the main theorem, we're going to use criterion due to Groves and Manning. And so if you want to show that a group has this property of being virtually special cubulable, if you have a hyperbolic group that you're trying to show is virtually special cubulable, then all you need is an action. So I need an action of gamma on some cube complex where the action is co-compact So what's the difference between this and being cubulable? So for the cubulable, the action is supposed to be free and co-compact. Here you can have some stabilizers. And so you're going to need some condition on the stabilizers. So with stabilizers that are quasi-convex and are themselves virtually special cubable. Okay. Okay, so this is a more modest goal because now you can have some isotropy. You can have certain cells that are stabilized, and as long as you can control what the cells, what the stabilizers of the cells are, you can still get the result for gamma. Okay. Now, initially you might say, so the first thing you might say is, okay, if you're applying this process to a locally cat zero cube complex, there's already a cube complex there that you act on, right? So note, there already exists an action on a cat zero cube complex. Oh, here I should say cat zero cube complex, because when you do this hyperbolization, there's this map going the other way where, so basically this collapsing map here. Right? There's this map right here. When you form this via this pullback, there's a map from HY to Y. And so there's an action of pi 1 HY acts on Y tilde. And this here is a cat zero cube complex. All right. So why is that not helpful? Well, the problem is that this action here has a gigantic kernel. All right. So the action here, the kernel of this action is not finitely generated typically. So it's an extremely bad. And so it's hard to say anything from this action here because, the kernel is just too big. Quasi-convex. So this means that the inclusion, so it means that the distances basically get deformed in a controlled manner. So maybe let me. So you have your. So let me say, yeah, thanks. So quasi-convex means that distances are distorted by some controlled amount. So if you've got a pair of points, so C distance x, y plus k, C distance x, y minus k. So here are for some constants, I guess C greater than or equal to 1 and maybe k. Okay. And then quasi-convex is if the inclusion is a quasi-symmetric map. So this is here. So this is quasi-isometric. And quasi-convex is if the inclusion map is quasi-symmetric. Is this okay? So there's an intrinsic metric that comes from the subgroup with its own word metric, and then there's an extrinsic one coming from the ambient word metric. Okay, so now let me go ahead and describe for you the construction of the cube complex that works. And so the idea here, so there's a few things to do. You need to construct this cube complex, check that the action is co-compact, so the cube complex with the action, check that the action is co-compact, and check these properties about the stabilizers. Okay. So the first step here is constructing cube complex. And so to motivate this, let me remind you of the standard way to subdivide a simplex into a cube complex. So there's the following subdivision. And so if you describe this process, what you're doing is, for a simplex, and the same works in higher dimensions, right? So the process here is you insert a vertex in every face, and then you connect vertices for codimension 1 inclusions. Okay, so I've got a vertex here, here. And then for each codimension 1 inclusion, I put in an edge. And then anytime I see the skeleton of a cube, one skeleton of a cube. So you insert cubes wherever you can. So if you do this for the simplex, right, you get this shape. Okay. Sorry? Which? Right. So there's, okay, so let me do this for this, right? So we're going to have a vertex for each of the vertices. We're going to have a vertex for each of the edges. And then each edge contains the two vertices adjacent as codimension 1. And so those are connected there. And then you have a new vertex for the two-dimensional face. That contains all three edges as codimension 1. So this is connected to the vertices for the three edges. And then anytime you see a 4-cycle, in this case, the perimeter of a square, you glue in a square. Okay. Now, you can do this anytime you've got a complex, polyhedral complex or CW complex. Typically, it doesn't give you anything very interesting. But if you do this, so carry out this process. If you carry out this process on the universal cover of this, so what I call it, I guess, that gives you a locally, and check that you get a locally cat 0. Cube complex. Okay. So let me explain this a little bit by drawing you maybe a picture of what. So let me do the example up. Maybe I'll draw it up here. So the example here, so let's say if y is just a single two-dimensional cube, so a square, and then h of y, I already told you looks something like this, maybe higher genus, but some surface with corners. And then h of y tilde now is going to look like, well, it naturally sits inside H2. And so I'm not going to draw this very well, but right. And you can picture, I guess, which way are the spikes going? The spikes should be going outwards. So something that, and each of these, and so on. Right. And it's like this region here. Is this okay? And you should picture each of these inside angles as being 90 degrees. So each of these are actually good. All right. So now what happens when you do this process? So now you're going to have a vertex. So I think maybe we call this script C of h of y tilde. So you're going to have one vertex. So maybe I'll just do it on the same picture. So you get one vertex in here. All right. Then for each of the vertices, so these are my zero-dimensional pieces in the cell complex. So I'm just going to do it on this part here. Then for each of the edges, so each of the one-dimensional cells, you get a vertex. And then what gets connected to what? So the top dimensional one contains all of these as a codimension 1. So notice already this is not going to be locally finite. The red ones each contain the 2 edges on either side as a codimension 1. And then the only squares you're going to see are each of these. Okay. And then you're going to see the same picture for each of these boundary components. So there's going to be, countably infinitely many of these. And each component here consists of countably infinitely many squares, each one adjacent to the next one. Is this okay? All right.
Was convexity here to choose this point, right?
So when if you look at the stabilizer of this vertex, the stabilizer of this vertex for the natural action on the cube complex will be exactly the fundamental group of HY. Okay. And the way you know that that's quasi-convex is because the subspace here is going to be quasi-convex in the whole thing. And so quasi-convexity then gets inherited by the corresponding group. So.
Convex, right?
Convex, yeah, it's convex. That's right. So, yeah, and then the group is quasi-convex. Yeah. Okay. All right. So what's the action then on this? So then there's an actual. So since pi 1 hy acts on hy tilde, there's an induced action on the C of hy tilde. So the action preserves this cellular structure. The action of the fundamental group preserves the cellular structure, so it moves these cells around, and corresponding to moving these cells around, you drag the cubes along with them. And so now there's a few things that one needs to check. So namely, you need to check that this is cat 0, need to check that it's co-compact. So co-compact is easy, but locally cat 0 is sort of interesting. So yeah, so co-compact is easy because if you quotient out by the action, you get C of y. So co-compactness is easy. So quotient is C of hy. And so if y is, if you started out with something that's a finite simplicial complex, then this thing here has only finitely many cells, and so it's a finite complex, finite cube complex. So this is easy. Locally, cat 0 is a little more interesting. So to check locally cat 0, you need to describe, look at the links of vertices. So the links of vertices for vertices V in C of hy tilde. So the link of vertices, it's basically, if you're not familiar with it, it's basically the space of local directions at a vertex. And so what you're going to see is it has a natural structure of a simplicial complex. So this is the simplicial. So this is a simplicial complex describing directions from V. And so if you want to think of it metrically, you could also think of it as just taking an epsilon ball, small epsilon ball centered at V, and just looking at all the points, epsilon sphere centered at V, and then looking at all the points there. Okay. And there's an easy criterion for being locally cat 0, so we need to check that. So need to check that the simplicial complex is flag. So this means that anytime you see a subset of a collection of vertices that are pairwise adjacent, it fills in to a simplex. So every subset of pairwise adjacent vertices span a simplex of the appropriate dimension. So where does flagness come from? So what one needs to do is one needs to try and understand what these links look like. And so the first thing is that there's a lemma that tells you that these links naturally decompose as a join. So the link, so notice that, so in the simplicial complex, in the cube complex C of hy, the vertices are either correspond to codimension 1 cells, or they can correspond to being included in a cell of dimension 1 higher. Okay. So we can decompose the link. So decompose link V into sets of vertices. So I think the ascending link and the descending link, where these correspond to collections of vertices where these are all cells containing the cell corresponding to V. And these ones here correspond to cells that are contained in the cell corresponding to V. Is this okay? All right. And then there's a few lemmas. So the first thing is that link V is a join of these. So join of flag complexes are flags, so then you can focus on each of these separately. And then so you can guess that, so lemma 1. So you can guess then what one does. So one shows lemma 2. If you look at the ascending link, so this here is isomorphic to the link of the cell corresponding to V. Okay, so for instance, if I'm on this edge here and I look at the ascending link, so let me just draw you the picture in here. So if I'm along one of these edges, so I'm taking this vertex that corresponds to this edge, and I look at the ascending link, I'm going to get vertices pointing into each of the cells that passes through that edge. Okay. And that's naturally a copy of the link of the edge itself. Is this okay? So this one's not too hard. Actually, none of these are particularly hard. The third lemma is to check that the descending link V is flag. And this requires, so this comes from a Helly property for families of orthogonally intersecting hyperplanes in Hn. So let me just explain where this comes from. So if you're looking at the descending link, you have a given cell and all the vertices that are connected to it because they're contained in that cell. All right. So for example, if you're at this vertex here, the descending link is everything. Okay. And what we're trying to figure out is if you've got a bunch of these one-dimensional things that pairwise intersect, right? So are going to be connected, then do they fill in a cube? And so the point here is that any two of these that are connected by an edge, they come from a little square, which means that the corresponding codimension 1 guys have to intersect. And then if you know that every pair of orthogonally intersecting hyperplanes, if you have that property that they all share a common intersection, that then gives you a cube, a vertex at the bottom corresponding to that intersection, where everything lies on the common cube coming up that contains this entire picture. I'm not describing that very well, but if you draw the picture, it becomes kind of... Okay, so this is how you get, how you check the flagness condition, and then that tells you then that this cube complex is locally cat 0 and then globally cat. So then to check globally cat 0, there's one other thing that you need. So this gives locally cat 0. To check globally cat 0, that's also not too hard. So let me put that as maybe a proposition. So in the paper, we actually so this verifies locally cat 0. So the only thing that you're left with is checking that the fundamental group is trivial. And so the proposition then is that pi1 of C of H, Y tilde. It's trivial. And in the paper, we did this by path reduction. So we basically started with a long path and then showed that you could repeatedly reduce the path, make it shorter and shorter, until eventually it was down to a point. But there's another maybe easier conceptual way to think about this, which we didn't realize until after. So if you think about how the cube complex is constructed, it's constructed by taking these spaces, the C of so maybe I'll write it here. So C of H, Y tilde is constructed by assembling copies of C of H of cubes where you're basically, again, replacing each copy of the universal cover of the hyperbolization of a cube by a corresponding cube complex. And then you're attaching them together in exactly the same manner. Okay? So you first showed that these guys here are contractible. And then what you see is that both spaces C of HY tilde and HY tilde are constructed by assembling contractible sets with exactly the same combinatorics of intersection. And then a nerve argument then tells you that these two things, that if one of these is simply connected, then the other one also has to be simply connected. Does that make sense? So yeah, we didn't notice that until after after the paper was out. So, but I think conceptually it makes it a little easier. Actually, this had been showing. This was something that took us a fair amount of time because yeah, the path reduction argument is not so straightforward. So, but yeah, okay. So let's see. So then the last couple things that one needed to check. So we needed quasi-convexity. So quasi-convexity, I think, as we mentioned. So cell stabilizers. So stabilizers of cubes in C of H, Y tilde are always conjugates of, well, so pi 1 of H of a cube of some dimension. So basically, if you stabilize like a vertex, you're essentially it's just the isometries that preserve this cell, and that's a copy of pi 1 of H of the corresponding thing. For a cube, it's a little bit trickier. So you remember I mentioned there's like a ascending link and a descending link. So each of these cubes inside this cube complex also comes labeled with dimension of the corresponding cell. It turns out that the cubes have a unique vertex with minimal label, and the stabilizer of a cube ends up being just the pi 1 of that corresponding cell. So that's how you verify this. And so the point here is that so these are quasi-convex because the corresponding H del I tilde sits inside H Y tilde as a convex subset. And then the last thing was, so let's see, so we needed quasi-convexity. Oh, and you need, and these are, and are virtually special cubable. Because they also sit inside one of these lattices of simple type in SON1, and those are known to be virtually special cubable. So it sits as a quasi-convex subgroup inside this lattice. The lattice is virtually special cubable, and so the quasi-convex subgroup, which is this guy, is virtually special cubable. And that checks all the ingredients you need. Okay. So I'll stop here.